Hello. Welcome to the latest in our series of webinars featuring science from the Green Bank Telescope and news from the Green Bank Observatory. I'm Jay Lockman, and I'll be hosting the session today. Let me start with just a few quick items of observatory news. We will have quite a presence at the AAS meeting upcoming in New Orleans, so please stop by our booth and talk to the staff if you have any questions or just want some more information about the Green Bank Telescope. And also, don't forget that the next call for proposals has a deadline of January 31st, which is a Wednesday, and we'll be accepting proposals then for the second half of 2024. Our speaker today is Andy Fox from Space Telescope Science Institute. He'll be talking to us on the metallicity of compact high-velocity clouds. Let me remind everyone that the webinar is being recorded, and if you have questions, please submit them using the Q&A button in the lower part of your screen, and we'll get to them at the end of the webinar. Take it away, Andy.
Thanks very much, Jay. It's great to be here with you at the Green Bank Community Science webinar. Let me share my screen and we will get going. So I'm going to be talking about the metallicity of compact high-velocity clouds, and the subtitle to this presentation is Clues to the Assembly History of the Milky Way. And I work at Space Telescope Science Institute and Johns Hopkins University in Baltimore. I'd like to begin by acknowledging the collaborators who I've worked with on much of this work on high-velocity clouds at different institutions. And I want to give a special shout out to the folks who have been in postdocs working with me in the Milky Way Halo Research Group at Space Telescope. A lot of this work I'll be discussing today has happened in this research group and with our collaborators. So like all spiral galaxies, all massive galaxies, the Milky Way has a halo, an extended region around the disk. We use the term circumgalactic medium as well to describe this volume going out to large distances from a galaxy. And the halo is an important part of the entire galaxy evolution cycle. In particular, we look at the inflows and outflows that pass through the halo of a galaxy. And they play very important roles in the baryon cycle. They bring in new material, new gas that can ultimately form stars. They affect the chemistry of the galaxy because they bring in low metallicity gas, and high metallicity gas can be expelled. And we also see circulation of gas in so-called galactic fountains, where gas moves out from the disk and then eventually falls back down, as well as streams of gas that can come off satellite galaxies like the Magellanic Clouds. So these processes are really important for moving baryons around and for setting up star formation. So we really think of the halo as an important component of a galaxy where these processes happen. And in the Milky Way, we have this great opportunity to study these gas transport processes, these inflows and outflows up close in high resolution and with great detail with many different data sets. So if we want to study the Milky Way halo and look at this baryon cycle in our galaxy, one of the best ways we can trace the Milky Way halo is through so-called high-velocity clouds. These are clouds moving at velocities too fast to be explained by the disk, by a rotating disk, which in practice means about 100 kilometers per second or more in terms of their absolute velocities. So this is an all-sky map from the Hi4Pi survey, following earlier H1 surveys such as LAB and GAS, that just shows the high-velocity clouds across the entire sky, here with the anti-center at the center of the projection. And we can see here a snapshot of the neutral gas, the H1 emitting gas, in our own halo. We're really seeing what a galaxy halo looks like, at least in neutral gas, from the inside out. And you see there's a lot of structure and a lot of various complexes which are visible here that are telling us about the inflows and outflows in the Milky Way at the current time. So there's a very rich data set in high-velocity clouds that's telling us about these inflows, these outflows, and about the baryon cycle in the galaxy. Now, these clouds were discovered at 21 centimeter in the 1960s or so. So we've been studying them for a long time in neutral gas. But what we've realized more recently is that HVCs should really be thought of as multi-phase clouds, in particular with a lot of ionized gas as well as the neutral gas. And we know that in large part because of UV spectroscopy, where we can point UV telescopes, such as Hubble, towards quasars that are all over the sky, and we can look for absorption in UV metal lines. And that absorption can trace these high-velocity clouds in the UV. In particular, it can trace the ionized gas that we don't see in the H1 surveys. And Hubble has pointed its UV spectrographs at hundreds and hundreds of AGN now in different parts of the sky. And each circle you see on this figure shows a Hubble pointing where we've looked for UV absorption at high velocities. And they cover very large parts of the sky. In fact, if we look at the numbers, right, the covering fraction of the sky at high velocities, if you look in 21 centimeters with H1, you find about a third of the sky is covered. So a substantial amount. But that number goes up much higher when we look with these UV lines. If we look in silicon-3, 1206, which is a strong UV metal line, we find a covering fraction of over 75%. So most of the sky, if you take a random sight line through the Milky Way halo, is covered by this fast-moving gas. It's a very widespread phenomenon. These are not rare clouds. They're found all over the halo of our galaxy. So two of the properties of these clouds that we're really interested in are distances and metallicities. Distances, of course, telling us how close to the plane of the galaxy are they, and metallicities telling us about their chemical enrichment. How much metal enrichment has there been? Now, there's a big bias here that we've tended to study the large clouds. That's natural because they're larger on the sky, they're easier to find background targets and to measure these things. But if you look at the big complexes, the large named high velocity clouds, these ones tend to be fairly nearby, meaning within 10 or 20 kiloparsecs or so. There is one notable exception, which is the Magellanic Stream. That may be further away at 50 kiloparsecs or so. But the other clouds where the distances are measured, they tend to be pretty close by, right? So we're really seeing the inner halo of the Milky Way. These distance measurements place these clouds here, as you can see, between 10, 20, 12 kiloparsecs, in that kind of ballpark. So we're not seeing the outer halo, we're seeing gas pretty close in towards the disk in these clouds. We also see a range of metallicities, and I'm going to talk more shortly about new metallicity range measurements in these clouds. But we see, for example, Complex C, that's a large HVC in the Northern Hemisphere, that's down at about 20 or 30% solar. The Smith cloud may be a little higher, about half solar abundance, whereas Complex A is down at 10% solar. So there is a range of metallicities in these clouds, suggesting a range of origins, right? Some of the clouds are more metal enriched than others, suggesting they've been processed more recently through star formation, where some of them have lower metallicities. But like I said, we've tended to focus on the large HVCs because they're big, they're easy to study, there's more data on those. But there's a lot of smaller clouds up here in the high velocity sky where we don't have distance measurements, and we don't really know where they are. And that's what I want to talk about for the rest of this presentation. It's the compact high velocity clouds, the small ones. And when we say compact, we mean less than about 2 degrees in angle on the sky. And I want to present some results from a recent program using the Green Bank Telescope and the Hubble Space Telescope that has looked at the metallicity of these clouds using a decent sized sample, meaning more than 1 or 2, which is what we had in the past. So what we did is we found 5 compact HVCs using a gas high velocity cloud catalog that had bright background targets behind them. And the reason is then we can point Hubble with its UV spectrographs at these clouds to measure their metal absorption. So we had to start by cross-correlating the cloud catalog with the quasar catalog. And that's how we formed this sample. And this is the location of where these 5 clouds are on the sky. They're all in the southern hemisphere, pretty close to the Magellanic system, the LMC, the SMC, and the Magellanic Stream. If you show this on a different coordinate system to deproject the South Pole, where you get these distortions, you can see where these clouds lie, these 5 directions relative to the Magellanic system. So we're in the southern sky here, and we've identified these 5 clouds in that part of the sky. And here are the H1 intensity maps of these clouds. This is from Hi4Pi data. And so you're seeing these 5 clouds. They're fairly compact and in most cases, there's one main H1 component, but you can also see there is some substructure here. There is some clumpiness and smaller components in there. But so these are the 5 clouds that we have studied where we found a background source, and that's shown in each panel with that white star, which is the UV bright target that we can use for a Hubble observation to get the UV spectroscopy. So we do that for these 5 clouds, and I'm going to show you some data here. And this is the one of the main results. The top panel in each of these pairs of plots shows the GBT data on the 21 centimeter spectrum. The lower panel shows a metal line of neutral oxygen in the UV data from Hubble. This is with the COS spectrograph. That line of neutral oxygen is a great way of tracing the metallicity. And that's because oxygen has a very small ionization correction, meaning it's coupled very closely to the hydrogen. So when hydrogen is neutral, oxygen is neutral. When hydrogen is ionized, oxygen is ionized. And because those two couple, it means you can get a very clean metallicity measurement by combining the O1 from Hubble with the 21 centimeters from the GBT. And I think this is a great example of an experiment that requires both the radio data from the GBT with the space-based data from Hubble. We couldn't do it with one or the other of those. We need both of them. So in each panel, you see the emission line from the H1, the absorption line in the UV, and please just look at the vertical pink lines there, which are the high velocity components. You'll see in each panel there's a lot of 0 kilometers per second gas, which is the Milky Way. That's our ISM, which we're not studying here. Just look at the high velocity component with the pink vertical lines. And in each case, we see the H1, we see the O1 at the same velocity. And that tells us we're seeing the same component. So this is a very simple measurement. What we do is we compare the oxygen and the sulfur and the hydrogen abundances just by measuring the strength of those emission lines, the strength of those absorption lines. And we can get out of that an oxygen abundance. And as I say, an oxygen abundance is a great indicator of the overall metallicity of the cloud. Other elements tend to deplete into dust or tend to have big ionization corrections. Oxygen, we think, does not deplete into dust. That's not seen in the ISM. So it's a clean indicator of the overall metallicity of the cloud, which is why we use it. So here are the results, right? Here are the 5 metallicities. And I should say this is in a paper that's accepted and is in press at the Astrophysical Journal. It's led by Tricia Ashley, who was a postdoc working with us on this. And she found these really interesting results. 3 of the clouds have very low oxygen abundances. Those are the ones in red here. These abundances are about 4% solar, 2% solar, and the other one also 2% solar. So very unenriched in their metal content. The other 2, which are the blue labels, are about 16 or 17% solar. Those are closer to the abundances we would see in Magellanic gas. Those are Magellanic type of abundances that we measure across the Magellanic stream and Magellanic system. So for those 2 slightly higher abundances, I think the easiest, most natural explanation of this is that we're seeing the Magellanic gas, like a clump of material from the Magellanic system. But the 3 low metallicity cases, those are much lower than we see in the Magellanic system. So it's not obvious that those are Magellanic clouds in those cases. They actually appear to be something else. And so I'm going to focus on these 3 really low metallicity clouds. So the question is, where do they come from and what is giving us those low abundances? Now, in addition to oxygen, we do have a number of other elements we can measure in the UV through their absorption lines, and these include sulfur, nitrogen, carbon, silicon, aluminium, and iron. So we have a wide range of metals to work with. The oxygen I've already shown you, those are these points here, where we're showing here the abundances on a log scale relative to solar. So 0 here means solar abundances, -1 is a 10th solar, and so on. Now, with the other elements, we do have to apply ionization corrections. So we do a series of models with the cloudy photoionization code that accounts for the abundances in different ionization states from what's measured. And what I'm showing you here is the corrected abundances once we've taken into account those ionization corrections. And there's a lot of data on here, but what I want to show you is just to look at 3 elements: carbon, silicon, and aluminium. When you look at the levels of those 3 elements in these clouds, they are less abundant than oxygen. They are lower down on this plot in on the log axis than oxygen. In other words, the carbon to oxygen, silicon to oxygen, and aluminium to oxygen ratios are all subsolar. Those elements are depleted in these clouds. And the traditional way we interpret that is in terms of dust. The idea is that carbon, silicon, and aluminium are known to deplete onto dust grains in the interstellar medium. We see that in our own galaxy and other galaxies, whereas oxygen does not. So oxygen is telling us about what's in the gas phase, and the amount by which these are depleted out of the gas phase for carbon, silicon, and aluminium gives us an indication of how much dust there is. So it appears there is some dust in these clouds as well as their lower abundances, and that's another important clue for where they came from. But the important question I want to ask you is, well, what are these clouds and where are these clouds? We have shown that in 3 of these 5 cases, the abundances are extremely low, between 2 and 4% of the solar value. And that's much lower than we see for clouds that are near the Milky Way, where things tend to be more metal enriched. So where are they? I don't think we've really answered that question completely, but we have a few ideas, and I want to run through them with you. So the first suggestion would be, well, could they be somewhere in the inner halo of the Milky Way? And when I say inner halo, I'm saying let's say within 50 kiloparsecs or so. So you can just imagine schematically, here's our Milky Way. Could you place these clouds somewhere up there in the halo? Well, there's a couple of problems with this. One, as I said, is that the clouds that we do know of in the inner halo, they tend to be higher metallicities, at least 20 or 30% solar, sometimes higher. So that's a sort of order of magnitude higher than we're measuring in these low metallicity clouds. The other challenge with this model is that we know the Milky Way is surrounded by a hot halo, and that is X-ray emitting gas at 1,000,000 degrees Kelvin or higher. And that halo is itself metal enriched because we can see this in the X-rays and it's being measured. So it's not easy to come up with a way that you could put these low metallicity clouds inside this hot halo, because they would either be enriched through mixing, or they could just be ionized and evaporated as well by this interaction with the hot halo. So it's not easy to explain how could these clouds survive, these very low metallicity clouds survive when they're close in this picture. So it's hard to explain these clouds being very close to the Milky Way, given their very low abundances. So could you put them further away? The halo becomes less dense, the hot gas becomes less dense as you go further away. So could you put these clouds further at higher distance? That would actually solve the problem of why aren't they being evaporated? Or how can they have those low metallicities? Because in this case, they are then outside that metal-enriched hot halo. So that's a possibility. And we think that's one viable model for what's going on here. But you could go further and say, well, could they be somewhere in the local group? I mean, once you get beyond a few hundred kiloparsecs from the Milky Way, you're really talking about local group scales. I mean, M31, the other big spiral in the local group, is about 700 kiloparsecs away. So, on that scale, you might start thinking about, are these local group clouds rather than something associated just with the Milky Way? The problem there is that if you start to put them too far away, these clouds become unreasonably large. Remember I said they're defined as being 2 degrees or less on the sky? If you put 2 degrees at 300 kiloparsecs, that cloud is then bigger than a dwarf galaxy. So in other words, these H1 clouds would have to be bigger than a dwarf galaxy, but yet they don't have any star formation, because these are starless clouds where no stars or stellar counterpart has ever been found. So it becomes very difficult to put these things too far away. They become too large, and they also become too massive. And then the question is, well, why haven't they formed stars? So of these options, it seems that somewhere in the outer halo is probably the more likely explanation, right? These clouds have to be far enough away to survive and to maintain these low metallicities, but not so far away that they're very massive and ought to be forming stars. That's the difficulty here. So that's the question of where are the clouds? The related question, and maybe even the harder question, is, well, what is the origin of the clouds? What are they? Where did they come from? Again, we don't know the answer to that. We have several possible ideas that we're looking at. Could they be stripped gas from dwarf galaxies, right? Small galaxies can be stripped of their gas through tides or through ram pressure, and that can leave some of this remaining gas hanging around. So are we seeing this leftover debris from stripping with satellites in the halo? That's a possibility. Could they be so-called mini halos? These are what are they're small dark matter halos that are starless, but they may have some gas in them. And gas with no stars is basically what we're seeing in these compact HVCs, and it's unenriched gas with no stars. So there are these models out there, work from Martin Rees and from Braun and Burton, who have looked at these mini halos and wondered, could these be these sort of leftover dark matter dominated halos that are still hanging out somewhere in the local group? Or is there any other way of explaining this? I think we need to keep looking at this. We need more data, we need more metallicity measurements, and we need deeper surveys for the stars. I mean, if this was stripped from a dwarf galaxy, the natural question is to say, well, where is that dwarf galaxy? We haven't identified any in existing surveys to find these. So I think this is still an open question. But I would end this part of the talk by saying we think the Milky Way and the local group are still evolving, right? We shouldn't think of the Milky Way as a finished product. There is no such thing as a finished galaxy. They continue to evolve. They continue to accrete gas from their surroundings and circulate it around. And so maybe some of this is this leftover gas that's been out there for a long time, far in the outer reaches of the Milky Way halo. I think it's giving us clues that the formation of our galaxy is still ongoing. It's not a finished process. So I'm going to end here, and I'd like to leave some time for questions and discussion. So the bullet points I'd like to leave up are here. The first part is this overview of high velocity clouds in general, that we see them all over the sky with high covering fraction, and they're telling us about inflows and outflows. And then the new results are based on these GBT and HST metallicities in compact clouds. Out of the 5 clouds in our sample, 2 of them could be explained by just gas in the Magellanic system, but it's the 3 low metallicity clouds, which are much lower than Magellanic metallicities, that are really telling us something else. And it's an ongoing question to figure out what these clouds are. It does look like they have to be somewhere in the outer halo, but we do have more work to do to figure out exactly what their origin is and where they come from. And with that, thanks for your attention. It's been great to give this seminar, and I would be very happy to take any questions.
Thanks very much, Andy. This is really quite interesting. And let me just remind everyone to submit questions through the Q&A box in the lower part of the screen, and also that this recording of this talk will be available within a day or so through the Green Bank Observatory website. And let me ask, some questions have come in. Can the velocities of these, quote, high velocity, unquote, clouds be used to determine the amount of dark matter in the Milky Way, i.e. the escape velocity?
That's a really interesting question. I think the answer is that would be difficult, because if the velocities were just tracing gravity, then we could do that. If these were just gravitational motions, these clouds were following the potential well, we could then use that to back out the mass of the dark matter halo of the Milky Way. But the problem is it doesn't look like their velocities are gravitational. It's not just gas which is falling in under gravity. It's gas that appears to be pushed out by supernova explosions, gas that may be coming from interactions between our neighbors, like the Magellanic clouds. So there's all these other processes that push the gas around, which means the velocities we measure, and it's true these have high velocities and we can measure those well, but they don't necessarily tell us about the gravitational field of the Milky Way, because there's all these other ways you can accelerate and decelerate the gas. So that's why we tend not to interpret their velocities in terms of dark matter masses, is that we can't say for sure, and it's probably unlikely that these are gravitational motions. There's other processes that are moving the gas around.
Okay, and another question. Can the dust in high velocity clouds be detected via infrared emission or shorter wavelength extinction?
Yes, that's another great question. There have been searches for infrared emission from the dust in high velocity clouds, and they have found there isn't much there, maybe a few detections, but not a lot of dust. Certainly not a lot compared to the disk, the ISM, the interstellar medium of the galaxy, for example, where there's plenty of dust and you can see it very clearly in the infrared. So it's certainly something that groups are doing. The difficulty is that these clouds are mostly metal poor compared to the Milky Way, right? I showed you some of the metallicities earlier. And when the metallicity is lower, the dust content tends to be lower too, because dust grains are mostly made up of metal atoms. So when the metallicity is lower, the dust content is lower, which means there isn't much dust in them that you could see in infrared thermal emission surveys. So So people have looked, yes, and found there's a couple of detections in the infrared, but it's a challenging measurement because the dust content is low to begin with. So you're looking for a very faint signal. And because that signal is so weak in the infrared, that's one of the main reasons why we look for dust in the UV. And I showed you those depletion patterns where you compare the abundances of different elements in the UV and compare them to oxygen. That's why we do that, is for this reason, is that if you try and look for the dust directly in the infrared, it's just very faint. And so you're looking for a very difficult, very weak signal.
Okay, on another topic, could the dark matter mini halos model possibly be determined by background object lensing?
Yes. Could the dark matter be measured by background lensing? Yes. I mean, I think if you had the right background object that happened to be behind it, that could potentially work. It's a very novel idea. The difficulty with all these experiments is that you're kind of requiring on luck to have a background target right behind the cloud that you're interested in. And that's why I showed you when we determined our sample and put the sample together, we found 5 clouds. We would love to have found more than 5. If we'd had 50, we would have proposed for them. But the problem is that you're taking a very small cloud on the sky and you're saying, I need a background quasar that is right behind it. And the smaller the region of the sky you look at, the fewer targets you're going to find, right? So we were able to find 5 that where we could find that background target because the clouds are very small in the sky. And so that's the same challenge you would face if you wanted to look for background lensing. I think it's a great idea, but there aren't going to be many targets that happen to be right behind. If you find one, maybe you're in luck, but I think that's the difficult part.
Okay, here's a question now that came in 2 pieces. Most of the observed halo X-ray emission comes from less than 2 kiloparsecs away, so you don't have to put the small clouds all that far away to avoid it. Could these clouds be accreting from the IGM? And then the second part is, that isn't to say that there's not more hot gas further out, but the density or temperature are just too low for observable X-ray emission.
Yes, I think that's a good question. We don't know very precisely how the X-ray emitting gas is distributed in the outer halo or even the inner halo, but much of it may be more nearby, as that questioner points out. Yes, it's a good point. There are also X-ray absorption measurements as well as X-ray emission, and those also point to a hot halo extended around the Milky Way. Exactly how far out it goes, I agree. We don't really know. Maybe we have some constraints or some models of that, but it's not an easy measurement to just see how far out does that hot gas go. So it's a fair point. I mean, whether you can put these clouds closer in, it would be easier to do that if there isn't much hot gas there. That's true, right? Because the hot gas can enrich the clouds or it can destroy the clouds through evaporation and so on. So if there's less hot gas around, maybe you can put some of these clouds nearby. But again, as I said, we don't, the confirmed clouds that are nearby all have metallicities that are much higher, maybe 20%, 30%, 50% solar, rather than 2 to 3%. And so that's the other reason that we're arguing for maybe more distant origin, is that these things are really much less metal enriched than the clouds that we know are nearby. I mean, that doesn't prove that they have to be further away, but they certainly have lower abundances than the known clouds, which is the other thing we have to explain.
We have a number of questions coming in, and we're about to run out of time. So let me just remind everyone that Andy will receive all the questions submitted, even those which he doesn't have a chance to answer here online. And so as a final question, oh gosh, 2 really interesting ones. It's interesting to present metallicities relative to solar. Might it be better to compare it to primordial metallicities? These clouds still appear to have participated in star formation.
Yeah, I think that's a great point. I think, yeah, I mean, comparing it to solar, I mean, there's nothing special about our sun, right, compared to other stars. So having a more general abundant system compared to primordial, I think that's an excellent idea. I mean, the reality is a lot of people in the field still quote abundances relative to solar. It's just sort of a standard thing. So I think people are doing it because everyone else is doing it. But I agree that it's not the only way of doing it, right? You can use absolute abundances rather than relative to solar. It does make it easy to describe. I think if we say, this cloud is half the solar abundance, I think people instinctively know what that is. So it does have the benefit of at least being easy to grasp and understand. But I do agree. I mean, I think from a physical standpoint, a primordial or an absolute abundance would make a lot of sense. Yeah.
Okay, at the risk of going a minute over, let's try one short final question. What is keeping these three clouds compact?
Another great question, because yes, that gets into the question of pressure support and what's keeping them compact. I haven't had time to get into that. In fact, that's not really something we looked at in this paper, but it's a very good point. I mean, the further away they are, then the density of the Milky Way corona, the surrounding gas, should be lower, right? Which means the pressure should be lower. So there should be able to, it's easier for a cloud to expand when it's far away on the outer edge of the halo than close in. So that is another factor in this discussion, is what's pressure supporting them. I don't know is the short answer. But they are they're not particularly high pressure compared to like an ISM cloud. So you don't need much to confine it. These aren't, very high pressure objects like you sometimes find in the ISM or the disk of galaxies. But certainly I agree. It's a good point that pressure support is another piece of this puzzle in trying to figure out where they come from. Yeah.
Unfortunately, we've run out of time before we've run out of questions. And so, as I said, Andy will receive the list of questions that were asked, even if he's unable to answer them now as we reach the end of our webinar time. Let me thank all of you for attending today and remind you that in 2 weeks, we'll have the next of this series. January 3rd, Mike Shull will be speaking about the high latitude interstellar medium, dust and gas in the galactic halo. We hope that you'll be able to join us then. Thank you and goodbye.
Thank you.